What if I told you that an object from another star system is passing through our solar system right now? Not a spaceship, not science fiction, but a real comet 3IATLAS with a sudden 20 times brightening, a strange green glow, and chemistry unlike anything seen in our solar system. As it approaches Mars, orbiters like MRO, MAVEN, TGO, and HOPE will capture this visitor from a vantage point Earth alone cannot provide. Its unpredictable flares, alien-like chemical composition, and passage near another planet make it one of the most fascinating astronomical events in decades. Is 3IATLAS merely an unusually active comet, or is it something more mysterious? Could its alien chemistry hint at conditions in a distant star system, or perhaps reveal processes we've never observed before? The universe is vast, and sometimes it sends a messenger from beyond the stars to remind us just how small yet connected we really are, a stranger in our solar system. The night sky is vast, stretching beyond comprehension, a tapestry of light and shadow, stars and darkness woven together across billions of kilometers. Most of what we see is familiar, the planets tracing their orbits, stars that have burned for millions of years, constellations mapped and charted, predictable and comforting. And then, occasionally, the universe surprises us. Something appears that does not belong. A visitor from another world. A fragment of another star system. Something that moves differently, glows differently, behaves differently. This is the story of 3IATLAS, the third interstellar object ever detected, a comet unlike any we have observed before. Unlike ordinary comets, born in the Oort cloud or the Kuiper belt of our own solar system, 3IATLAS carries the signature of a distant sun, a chemical history formed under conditions far removed from our own. It arrives silently, unnoticed at first, just another faint point of light drifting through the immense blackness. And yet, to astronomers, it immediately stood out, a traveler from the stars, rare and precious, passing briefly through our cosmic neighborhood. The I in its name signals its origin: interstellar, hyperbolic, open-ended, moving too fast to be captured by the sun's gravity. 3IATLAS will never return. Once it departs, it is gone forever, lost to the void, continuing its solitary journey through the galaxy. Only a handful of interstellar visitors have been spotted in all of human history. Oumuamua in 2017 startled scientists with its strange elongated shape and unexplained acceleration. Borisov in 2019 resembled a familiar comet, yet it too carried anomalies that hinted at conditions far beyond our Sunday. And now, 3IATLAS appears, brightening and flaring in ways that defy expectations, hinting at the strange chemistry and dynamics of an alien world. From the moment it was discovered, in July 2025, by the asteroid terrestrial impact Last Alert System in Chile, astronomers recognized that this was no ordinary comet. Its trajectory is a perfect example of interstellar dynamics. Unlike Earth-orbiting satellites or solar system comets bound by elliptic orbits, 3IATLAS follows a hyperbolic path. It is a messenger in motion, moving at speeds that suggest it originated light years away, ejected from its home system long ago, wandering through the galaxy for millennia. And now, by a chance that borders on cosmic poetry, it is passing through our celestial backyard. At first, it appeared faint, unremarkable, but careful monitoring revealed something unusual. 3IATLAS was brightening far faster than predicted, a surge in luminosity that startled observers. By early September, it had become 20 times brighter than theoretical models suggested for a comet at its distance from the Sunday. This sudden flare transformed it from a distant speck into a beacon, visible to sensitive instruments across the globe. Scientists scrambled to redirect telescopes, from Chile to Hawaii, from Earth-orbiting observatories to space telescopes, all focused on a single point of light racing through the void. The initial outburst was just the first clue that 3IATLAS is unlike anything we've seen. Ordinary comets glow when solar heat causes their ices to sublimate. Water, carbon dioxide, carbon monoxide, methane. These ices vaporize, releasing gas and dust that reflects sunlight, creating the iconic coma and tail. But 3I/ATLAS's early behavior did not fit any known pattern. Its sudden greenish hue hinted at chemical processes alien to the solar system, while its emissions of carbon dioxide and nickel suggested a composition unfamiliar to astronomers. Already, we were looking at a visitor that might challenge our understanding of cometary physics, chemistry, and the conditions of planetary formation beyond our star. Then came another factor that captured the imagination: its trajectory toward Mars. While still tens of millions of kilometers away, predictions indicated that 3I/ATLAS would pass unusually close to the red planet in early October 2025. For orbiters already circling Mars, NASA's MRO and MAVEN, ESA's TGO, and the UAE's HOPE probe, this meant a chance to study the comet not just from Earth, but from a second vantage point in the solar system. Mars, for once, would not be the observed, but the observer, a platform offering a unique perspective on a celestial visitor from another star. The story of 3I/ATLAS is both scientific and philosophical. On one level, it is a chance to study interstellar chemistry, to analyze isotopes, molecular abundances, and outgassing behavior in a way that has never been possible before. On another level, it is a reminder of our place in the galaxy. Earth is not isolated. Our solar system is not a solitary island. Objects like 3I/ATLAS carry with them the fingerprints of other suns, the chemical history of alien planetary systems. They offer a fleeting, tangible connection to worlds we may never visit, histories we can only infer, and processes that unfold across distances so vast they defy imagination. The anticipation surrounding 3I/ATLAS is palpable. Astronomers are racing to measure every variation in brightness, to record every spectral line, to detect any jets of gas or dust that may indicate rotation or structural instability. Amateurs with telescopes are joining the campaign, hoping to glimpse this interstellar wanderer, to capture a point of light that has traveled light years to reach our skies. The comet's very existence is an invitation to curiosity, a reminder that the cosmos is neither silent nor static, but alive with motion and possibility. Some have speculated wildly about the nature of 3I/ATLAS, wondering whether its unusual behavior could indicate technology, a probe from another civilization, or something even stranger. These ideas, though sensational, underscore the point. The universe does not always conform to our expectations, whether natural or artificial. 3I/ATLAS has captured our attention because it is different, because it defies easy categorization, because it challenges our assumptions, and in doing so, it reminds us of the humility and wonder inherent in astronomical discovery. As the comet continues its journey, approaching Mars, brightening, flaring, and glowing with an alien hue, the world watches. Data streams from telescopes on Earth, from orbiters above, and from instruments in space converge to create the most comprehensive portrait of an interstellar comet ever attempted. Each measurement, each spectrum, each image adds to our understanding, not just of 3I/ATLAS, but of the galaxy itself. It is a story of connection across the void. A comet born around another sun, traveling for eons, now intersecting the solar system for a brief, breathtaking moment. 3I/ATLAS is, in every sense, a stranger in our solar system. It is both familiar and alien. It glows like a comet, behaves like a comet, yet its chemistry and trajectory hint at worlds we have never seen. Its sudden outbursts and peculiar green light challenge our models and invite speculation. It passes near Mars, offering a chance to observe it from a perspective never before possible. And it will continue on its hyperbolic path, never to return. And yet, in this brief encounter, we are reminded of the scale and diversity of the galaxy. For every 3I/ATLAS we detect, countless others drift unseen. Every star system ejects icy fragments, planetesimals, and comets into the interstellar medium. And sometimes, by chance, one of them crosses our path, reminding us that our solar system is not alone, that the universe is filled with wanderers, and that discovery is always possible, even in the vast silence of space. This is the story that begins our journey. The story of a stranger in our solar system. a visitor from the stars, a comet that glows, flares, and challenges our understanding. Its arrival sets the stage for questions, mysteries, and revelations that will unfold in the chapters to come. It is a story of light, motion, chemistry, and wonder. A story that begins with a single point of green light racing across the void and promises to illuminate the vastness of the cosmos in ways we could scarcely imagine. Sudden outburst, 20 times, brightening. By early September 2025, the subtle, distant green glow of 3IATLAS had begun to change. The comet, once a faint point of light barely distinguishable against the night sky, was suddenly flaring. Its brightness surged to 20 times what astronomers had predicted, a dramatic increase that immediately captured the attention of observatories worldwide. This was no ordinary increase in luminosity, a predictable warming of ices under the sun's influence. It was a sudden, explosive event, a celestial flare that defied expectations. To understand why this outburst was so extraordinary, one must first consider what comets normally do. As they approach the sun, their frozen surfaces gradually warm. Water, ice, and more volatile substances, like carbon monoxide or carbon dioxide, sublimate, creating a glowing halo, a coma, and sometimes a long trailing tail. The brightness of the comet increases steadily, a predictable crescendo calculated through models refined over decades of observations. Most comets obey these rules with precision. 3IATLAS did not. Astronomers observing the outburst likened it to a quiet candle, suddenly transforming into a bonfire. Within days, its faint light became a beacon visible to instruments that had only just managed to detect it. The sudden flare was unexpected, especially given the comet's distance from the sun at the time over 2 astronomical units. Water ice should have remained largely inert at that range. Only more volatile compounds could sublimate. Yet the sheer scale of the brightening suggested that either a massive reservoir of ices had suddenly become exposed, or that 3IATLAS contained unusual compounds unknown in solar system comets. The initial reaction from the scientific community was a mix of excitement and skepticism. Could it be an observational error? Multiple observatories confirmed the surge in brightness independently, ruling out artifacts or misreadings. It became clear that the comet itself was responsible. Something internal to its structure, some process deep within its nucleus, had triggered this sudden eruption. Theories abounded. One explanation suggested that the comet's crust might have fractured, exposing fresh layers of volatile ice to sunlight. Another proposed that internal pressure from trapped gases had built to the point of explosion, venting suddenly into space. Yet another considered rotational forces. As the comet spins, regions of its surface experience stress, cracking, and releasing jets of material. Each theory had merit, but none fully accounted for the scale and timing of the brightening. Spectroscopy, the dissection of light into its component wavelengths, revealed more puzzles. The green glow suggested diatomic carbon C2, commonly responsible for the vivid green hue of comets. Yet the expected spectral signatures of C2 were weak or absent. Instead, astronomers detected unusual levels of carbon dioxide, cyanogen, and even trace amounts of vaporized nickel. Such a composition is unprecedented for a comet at this distance from the Sun. It suggested a chemistry unlike anything seen in our solar system, a fingerprint of its alien origin. The implications were profound. 3IATLAS was not just behaving differently, it was chemically alien. Its outburst provided the first real opportunity to observe the behavior of an interstellar comet under solar heating. What would normally be a steady, predictable increase in brightness became a dynamic, almost theatrical display. Jets of gas and dust spewed from the nucleus, creating asymmetries in the coma, hints of rotation, and subtle changes in its trajectory. The comet seemed almost alive, responding to the sun in ways that challenged existing models. Observatories on Earth adjusted their schedules. The Very Large Telescope in Chile, the Keck Observatory in Hawaii, and space telescopes like Hubble and JWST pivoted to track the comet in real time. Amateur astronomers too joined in, capturing streaks of green light across their cameras, contributing vital data points. Each observation added to a growing tapestry of knowledge, slowly revealing the complexity of this interstellar visitor. The timing of the outburst was also uncanny. The comet's increasing brightness coincided with predictions that it would soon pass relatively close to Mars, a chance for orbiters to observe it from a different perspective. From Earth, we could see its flare, but from Mars, spacecraft like MRO, MAVEN, TGO, and HOPE could capture finer details, from the structure of the coma to the jets of escaping gas. The universe, in its timing, had provided a rare and extraordinary vantage point for study. Scientists debated the mechanisms behind the brightening. Some emphasized structural collapse, suggesting that fractures exposed fresh ice layers. Others focused on volatile content, arguing that alien ices might sublimate more vigorously than anything in the solar system. Another possibility involved rotation. As the comet spins, uneven heating could trigger bursts of activity. Each explanation had evidence and counter-evidence, reflecting the complexity of 3IATLAS. Its alien origin added another layer of uncertainty. We could not assume that solar system models would perfectly apply. The sheer speed of the flare added drama. Within days, the comet's brightness increased to a level that made its green glow visible even to small telescopes. This sudden change drew attention not just from professional astronomers, but from science enthusiasts and the general public. Headlines quickly circulated. Alien comet flares unexpectedly. 3IATLAS glows green, 20 times brighter. And a stranger from the stars shocks scientists. The narrative of a mysterious, alien visitor captured imaginations worldwide. But the outburst was not merely a spectacle. It provided a critical scientific opportunity. Observing the sudden increase in brightness allowed astronomers to study the comet's nucleus indirectly. By analyzing changes in luminosity, spectra, and the morphology of the coma, researchers could infer the size of active regions, the composition of ejected material, and even the spin rate of the comet. It was a real-time laboratory for interstellar chemistry and physics, one that could yield insights no Earth-based laboratory could replicate. The outburst also forced recalculations of the comet's trajectory. Jets of material, unevenly ejected, can produce slight but measurable changes in the path of a comet. For a hyperbolic object like 3IATLAS, these effects are magnified, altering predictions for its closest approaches. Scientists meticulously tracked these changes, ensuring that models remained accurate for both Earth and Mars observations. Beyond the data, the brightening captured the imagination of theorists. Could this outburst hint at a comet with internal structure radically different from solar system comets? Could alien ices, formed under different stellar conditions, behave more explosively when exposed to solar heat? Each flare, each surge in brightness, became a test case, a challenge to the limits of our understanding. In the end, the sudden outburst of 3IATLAS serves as a dramatic reminder of the unexpected in astronomy. Even with centuries of observation, vast catalogs of comets, and advanced models, nature retains the power to surprise. A tiny green comet, traveling from another star system, had flared 20 times brighter than anticipated, transforming a faint point of light into a cosmic beacon. It announced itself to the world, signaling that our models are incomplete, our assumptions provisional, and that the galaxy still has secrets to reveal. This was only the beginning. The outburst set the stage for further discoveries as 3IATLAS approached Mars and perihelion, promising new surprises and insights. Scientists and enthusiasts alike watched with anticipation, knowing that this interstellar traveler had only begun to reveal its mysteries. Approaching Mars, a rare cosmic encounter. The vast emptiness of space is deceptive. To the naked eye, the universe appears mostly static, stars fixed in their constellations, planets slowly tracing their orbits, the occasional flash of a distant nova. Yet, behind this serene tableau, objects move at unimaginable speeds, bodies born in one system, crossing the void to reach another. Among these rare travelers, 3IATLAS is exceptional. Not only is it interstellar, but its trajectory brings it unusually close to Mars. A near pass that has astronomers around the world holding their breath in anticipation. On the 3rd of October 2025, calculations indicate that 3IATLAS will pass within 28 million kilometers of Mars. In cosmic terms, this is remarkably close, a hair's breadth on the scale of planetary distances. The comet will not strike Mars nor pose any threat, yet this proximity offers a once-in-a-lifetime chance to study an interstellar visitor from a vantage point far different from Earth. For the first time, humanity will observe such a comet not only from our planet, but from another world entirely. Mars, our planetary neighbor, has long been a source of fascination and exploration. Orbiters like NASA's Mars Reconnaissance Orbiter (MRO) and MAVEN, the European Trace Gas Orbiter, and the UAE's HOPE probe circle the red planet daily, studying its surface, atmosphere, and climate. Each carries sophisticated instruments designed for Martian science, high-resolution cameras, ultraviolet and infrared spectrometers, atmospheric sensors. And now, in an unprecedented turn, they will be redirected to observe 3IATLAS as it approaches, capturing its light, spectrum, and morphology from a perspective that Earth cannot replicate. The importance of this dual vantage point cannot be overstated. Earth-based telescopes face limitations. The atmosphere scatters and distorts light, weather interrupts observations, and viewing angles are fixed by Earth's rotation and orbit. From Mars' orbit, the same comet can be observed from a different position in space, providing data that complements Earth observations. Scientists can triangulate structures in the coma, analyze outgassing patterns, and resolve details that would otherwise be blurred or hidden. The comet's unusual behavior, its green glow, sudden brightening, and chemical anomalies makes this opportunity even more critical. Observing these phenomena from a closer perspective could reveal subtle jets, asymmetries in the coma, or transient events that Earth-based instruments might miss. Each observation could clarify the underlying mechanisms of the comet's unexpected activity, helping scientists distinguish between structural collapse, volatile outgassing, and potential rotational effects. The narrative of the encounter begins with preparation. Commands were sent to Mars orbiters weeks in advance. Cameras were reoriented. Spectrometers were set to scan specific wavelengths corresponding to known cometary molecules, carbon dioxide, cyanogen, and other volatiles. Mission planners coordinated to maximize coverage during the comet's closest approach, ensuring that multiple instruments could observe simultaneously. Data from MRO's high-rise camera, capable of resolving features as small as a meter, could capture the shape and size of the coma in exquisite detail. MAVEN's ultraviolet spectrometer could measure emissions from gases released in the upper layers of the coma. TGO's infrared instruments could detect temperature variations and chemical abundances. HOPE Suite added yet another perspective, giving a nearly 360-degree view of the passing object. Beyond instrumentation, the close encounter inspired awe in the astronomical community. Here was a comet that had traveled light years from another star system, now passing near another planet in our solar system, offering data of unparalleled richness. The scale of the event was humbling. For millennia, interstellar comets drifted unseen, unknown, silent in the darkness. Only in the last decade has technology allowed us to detect such fleeting visitors. And now, through a fortunate alignment, Mars itself became a platform for observation, expanding our observational reach into space. From Earth, astronomers monitored the comet's approach closely. Its brightness continued to fluctuate, hinting at ongoing outbursts or rotation. The green glow intensified as sublimation increased, releasing gases into space and producing faint jets along the nucleus. Observers tracked these changes nightly, refining orbital models and predicting the comet's appearance from Mars' orbit. The interplay between Earth and Mars observations promised a multidimensional understanding of the comet's dynamics, a level of detail never before possible for an interstellar visitor. As the comet drew nearer, simulations indicated subtle gravitational effects. Mars itself, while tiny in the comet's view, could influence the path of ejected material in the coma. Dust particles and volatile jets could interact with the Martian magnetosphere or solar wind in ways unique to the orbit. The possibility of detecting such interactions added another layer of scientific intrigue. Could the comet's outgassing generate localized plasma events? Could charged particles be tracked from orbit? Each question pointed to new avenues of research, emphasizing the value of this close encounter. The event also stirred the imagination of the public and media. Headlines described 3IATLAS as an alien comet or a messenger from the stars, emphasizing its strangeness and proximity to Mars. While scientists cautioned that there was no evidence of artificial origin, the narrative captured the human fascination with the unknown. A green comet, brightening dramatically, passing near a planet we have studied and longed to visit. These are the stories that inspire curiosity, wonder, and a sense of cosmic connection. The scientific and philosophical significance of this encounter cannot be overstated. Observing 3IATLAS from Mars provides a benchmark for understanding interstellar objects, their composition, structure, dynamics, and behavior under solar heating. It allows comparison with solar system comets, highlighting differences and similarities, and providing insights into how planetary systems form and evolve. Each data point gathered from this close approach informs models of planetary formation, cometary chemistry, and the diversity of exoplanetary systems across the galaxy. The comet's hyperbolic trajectory ensures that this event is fleeting. After passing Mars, 3IATLAS will continue toward perihelion, eventually swinging past Earth's orbit and continuing outward, never to return. The window for observation is therefore limited. Every image captured, every spectrum recorded, and every measurement taken is a precious record of a phenomenon that will not recur in human lifetimes. The alignment of Earth, Mars, and an interstellar comet is a rare cosmic coincidence, a gift to science and to wonder alike. In anticipation, astronomers and space agencies coordinated data sharing, ensuring that every piece of information would be available for study. The collaboration transcended borders, reflecting the universal nature of the event. From Chile to Hawaii, from Earth orbit to Mars orbiters, humanity collectively prepared to witness and record the passage of a visitor from another star system. The magnitude of this cooperation mirrored the significance of the event itself. As 3IATLAS approached its closest point to Mars, the green comet blazed against the cosmic backdrop, a glowing enigma streaking past the red planet. Its size, brightness, and chemical peculiarities drew all eyes upward. Mars orbiters recorded every detail, Earth-based telescopes confirmed every motion, and scientists pieced together the first multidimensional portrait of an interstellar comet observed from two worlds. It was an event of extraordinary significance, combining rare celestial mechanics with unprecedented observational opportunity. This encounter would leave a lasting impact on both science and imagination. For scientists, it provided a wealth of data, advancing our understanding of interstellar chemistry, cometary dynamics, and solar interactions. For the public, it offered a tangible glimpse into the workings of a galaxy far larger and more dynamic than everyday life suggests. And for the next generation of astronomers, it set a precedent that even the most distant wanderers from beyond the stars can be observed, studied, and understood if preparation and ingenuity align with the gift of timing. 3IATLAS, a stranger in our solar system, had transformed from a faint, distant point of light into a spectacle, a phenomenon, and a lesson. Its close approach to Mars was not just an event, it was a convergence of technology, chance, and cosmic mechanics, a rare opportunity to touch the edge of the unknown and bring its secrets closer to human understanding. Mars orbiters, ready for observation. The night sky over Mars is silent, vast, and empty to the human eye. But in orbit above the red planet, a fleet of robotic explorers waits, poised to witness an event that few could have imagined. For months, these spacecraft have circled Mars, their cameras trained on dunes, canyons, and volcanoes. But now, they will turn outward, toward the infinite blackness, to track a visitor from another star system, 3IATLAS. The spacecraft arrayed above Mars represents decades of human ingenuity. NASA's Mars Reconnaissance Orbiter, MRO, with its high-rise camera capable of resolving features less than a meter across, is a pinnacle of precision imaging. MAVEN, another NASA mission, carries ultraviolet spectrometers designed to study atmospheric escape, instruments now repurposed to probe the gaseous emissions of a distant comet. ESA's Trace Gas Orbiter. ESA's Trace Gasser, intended to analyze trace gases in Mars's atmosphere, will capture infrared spectra of the comet, measuring temperature variations and volatile composition. Finally, the UAE's HOPE probe, with its multispectral imaging system, completes the observational network, ensuring a near-complete picture of the comet's passage from this unique vantage point. From the moment the decision was made to observe 3IATLAS, the mission teams worked in concert. Camera angles were calculated, spectrometer settings optimized, and observation windows scheduled to maximize coverage. Unlike a comet approaching Earth, 3IATLAS would be moving at high speed relative to Mars, requiring precise timing and coordination. Orbiters had to adjust their pointing sequences, sometimes rotating or slewing their instruments to follow the comet across the sky. Every second counted. The data collection strategy was meticulous. HiRISE aimed to capture high-resolution images of the coma, revealing its shape, density, and any jets of dust and gas. MAVEN would measure ultraviolet emissions from molecules in the coma, particularly hydrogen, oxygen, and cyanogen, looking for chemical anomalies. TGO would record infrared spectra, focusing on temperature gradients and volatile outgassing, and HOPE would contribute broad imaging, capturing the global perspective of the comet's passage relative to Mars and the stars. Together, these observations promised an unprecedented multidimensional view of an interstellar object. Scientists anticipated several challenges. The comet's rapid motion meant that exposure times had to be carefully calculated to avoid blurring. Its unpredictable outbursts could create sudden changes in brightness, requiring real-time adjustments. Communication delays between Earth and Mars orbiters further complicated coordination, demanding pre-planned sequences and autonomous decision-making by the spacecraft. Despite these obstacles, the opportunity was too valuable to miss. The scientific goals of the observation campaign were ambitious. Researchers hoped to measure the structure of the coma, analyze the composition of gases being released, detect rotational features in the nucleus, and refine the orbital trajectory. These data would complement Earth-based observations, providing a second angle from which to study the comet's activity. By combining results from multiple platforms, scientists could construct a three-dimensional model of the comet's outgassing behavior, a feat never before attempted with an interstellar object. The comet's previous outburst, its sudden 20 times brightening, added urgency to the observations. 3IATLAS experienced another flare near Mars. Orbiters would have the chance to capture it in real time, revealing the mechanisms behind these explosive events. Could internal pressure from trapped gases drive the outbursts? Were structural fractures in the nucleus responsible? Or did alien chemistry create sublimation patterns unlike any solar system comet? Each observation would help answer these questions. The human element of this campaign cannot be understated. Scientists, engineers, and mission planners worked around the clock. Teams in mission control rooms in the United States, Europe, and the UAE coordinated schedules, exchanged real-time data, and made rapid calculations to optimize observation windows. The excitement was palpable. For the first time, a fleet of orbiters around another planet would study an interstellar object, turning Mars itself into a platform for astronomical discovery. As October 3 approached, the orbiters were ready. MRO's high-resolution camera had been tested and calibrated, MAVEN spectrometers prepped for the ultraviolet emissions, TGO's infrared system set to monitor volatile release, and HOPE's imaging instruments primed for wide-angle coverage. Together, they formed a network that would provide a multi-layered view of 3IATLAS, capturing its size, shape, chemistry, and activity with unprecedented clarity. The comet's approach was also an opportunity to study its interaction with the Martian environment. While the comet would pass at a safe distance, its outgassing could interact with the solar wind and the Martian magnetosphere. Scientists hoped to detect subtle plasma interactions, measure charged particle distributions, and observe how dust and gas behaved under different magnetic conditions. These insights could inform models of both cometary behavior and planetary magnetospheric physics. From Earth, telescopes continued to track the comet, measuring its brightness, color, and tail structure. The combined datasets from Mars and Earth offered a unique chance to compare observations from two vastly different vantage points. For the first time in human history, an interstellar comet would be studied from multiple planets simultaneously, providing the most complete picture possible of a visitor from another star system. The anticipation was electric. Amateur astronomers, scientists, and the public alike waited for images and data to arrive. Would 3IATLAS flare again? Would its coma reveal hidden jets or structures? Would its green glow intensify or shift in color? Every possibility was on the table, and each could provide critical insights into the comet's origin, chemistry, and dynamics. Beyond science, the observation campaign symbolized humanity's growing reach into the solar system. Mars, long a target of robotic exploration and dreams of human colonization, had become a platform for studying distant visitors. Instruments designed to study Martian geology and atmosphere were now turned outward, capturing the passage of an object that originated around another star. The event demonstrated how human exploration of one world can extend our understanding of the cosmos beyond. As 3IATLAS approached its closest point to Mars, the spacecraft recorded every moment. The comet's coma expanded. Its jets of gas and dust became more visible, and its brightness fluctuated in real time. The combined observations created a multi-dimensional portrait, revealing the alien chemistry hinted at in earlier Earth-based observations and providing new insights into its dynamic behavior. This chapter in the story of 3IATLAS Mars orbiters ready for observation represents one of the most ambitious astronomical campaigns in history. It demonstrates the synergy of planetary science and astronomy, the power of collaboration across continents, and the thrill of witnessing a truly alien visitor up close. Through these observations, humanity gained not just data, but perspective. The first, knowledge that we can study the unknown, even from a distance of hundreds of millions of kilometers, and that our technological reach continues to expand across the solar system. 3IATLAS had transformed Mars into a celestial observatory, a rare vantage point from which to watch a comet that defied expectations. And as it glided past, glowing green, flaring unpredictably, and revealing the secrets of a distant star system, scientists and observers alike understood that this was more than a comet. It was a messenger, a teacher, and a symbol of the cosmos's boundless mysteries. Speculation versus science. Whenever the cosmos delivers something unexpected, the human imagination reacts immediately. For 3IATLAS, a comet from another star system with its sudden flares, unusual green glow, and puzzling chemical composition, speculation has been inevitable. From the moment astronomers noticed its 20-fold brightening and alien-like chemistry, questions have swirled. What is this object really? Could it be more than a comet? Could its strange activity hint at something artificial? In the scientific community, caution dominates. Astronomers begin with observations, constructing models, and testing hypotheses. Every emission line, every brightness fluctuation, every change in trajectory must be measured, confirmed, and explained. Initial data from Earth-based telescopes showed unusual chemistry, depleted carbon chains, high levels of carbon dioxide, traces of nickel vapor, all unexpected in comets from our solar system. But these anomalies can often be explained through natural processes. Cosmic rays, interstellar aging, and exotic ice compositions can produce chemical signatures that seem alien but are entirely natural. Yet the public's fascination tends toward the extraordinary. News outlets and social media speculated that 3IATLAS might be alien technology, a probe, a derelict spacecraft, or even a fragment of a megastructure. These ideas, while provocative, highlight a fundamental tension between science and imagination. Science demands evidence. Extraordinary claims require extraordinary proof. Speculation, by contrast, thrives in uncertainty, filling gaps left by incomplete data with the possibilities our minds can conceive. Even within the scientific community, some voices challenge conventional explanations. Avi Loeb, a Harvard astronomer, has previously suggested that interstellar objects could include artificial structures or probes, noting that anomalies in cometary behavior may indicate design rather than randomness. With 3IATLAS, The argument is not that evidence of alien technology exists, but that its unusual properties, sudden brightening, inconsistent chemical signatures, green glow without expected molecules justify considering all possibilities. The debate exemplifies the delicate balance of scientific inquiry. On one hand, most of the data points to a natural explanation. The comet is composed of ices and dust formed around another star, ejected into interstellar space, now responding to the sun's warmth in ways that reflect its alien chemistry. On the other hand, its unexpected activity invites open-minded consideration. Could outgassing be unusually intense due to chemical composition unknown in the solar system? Could structural anomalies cause sudden flares? These questions are grounded in physics and chemistry, yet they also brush against the edges of speculation. To understand why speculation persists, consider the rarity of interstellar comets. Oumuamua, the first detected, had an elongated shape and accelerated in ways not fully explained by conventional physics. Borisov, the second, appeared more normal but exhibited unusual carbon monoxide ratios. 3IATLAS is the third, and it continues the pattern, an object from beyond our solar system behaving in ways that challenge assumptions. Each new visitor forces scientists to question what is typical for comets and opens the door to imaginative scenarios. Social media amplifies the mystery. Photographs of the comet's bright green glow, animations of its trajectory near Mars, and speculation about alien chemistry go viral. The narrative of a comet that looks alien resonates because it combines scientific novelty with the allure of the unknown. People are captivated not just by the data, but by the story. A tiny object traveling light years from another star, suddenly flaring in our skies, approaching another planet, and defying easy explanation. Despite the speculation, the scientific method prevails. Researchers focus on measurable quantities: the intensity of emissions, chemical abundances, jet structures, and orbital changes. They compare 3IATLAS to solar system comets and interstellar predecessors, noting both similarities and differences. Models are constructed to explain the sudden brightening, fractures exposing fresh ice, sublimation of unusual ices, rotational dynamics, and internal pressures. Each model is tested against observations, refined, and adjusted as new data arrives. From Mars orbiters, observations add an unprecedented layer. High-rise images resolve the comet's structure. MAVEN detects ultraviolet emissions. TGO measures infrared spectra. And HOPE provides wide-field imaging. This multi-point observation allows scientists to reconstruct the comet in 3 dimensions, analyzing jets, asymmetries, and outgassing patterns. Earth-based data complements these findings, producing the most comprehensive portrait of an interstellar comet in history. The interplay between speculation and science is more than academic. It influences how data are interpreted, how resources are allocated, and how future missions are designed. The upcoming Comet Interceptor mission, set to wait in orbit until the next interstellar object appears, is partially motivated by the lessons learned from 3IATLAS. If an unexpected flare or unusual chemistry appears again, the ability to respond, with spacecraft already positioned, could revolutionize our understanding of interstellar visitors. Yet, speculation remains a valuable tool. While extraordinary claims require evidence, considering unconventional possibilities ensures that researchers remain open-minded. It encourages creative thinking, hypothesis generation, and interdisciplinary collaboration. For 3IATLAS, the unusual brightening, green glow, and alien chemistry compels scientists to explore new chemical models, revisit assumptions about interstellar ices, and simulate extreme scenarios that would be impossible to test in a laboratory. As 3IATLAS passes Mars, the observations from orbit and Earth will clarify many questions. Yet even after detailed analysis, some mysteries may persist. How does the comet's chemistry compare to other systems? Are the flares driven purely by physics, or by chemical interactions we have not seen before? Does its alien origin create properties not found in solar system comets? Each unanswered question preserves a sense of wonder. Ultimately, speculation and science are complementary. Speculation inspires curiosity and imagination, motivating observation and creative modeling. Science tests, validates, and explains. Together, they allow us to confront the unknown while remaining grounded in evidence. 3IATLAS embodies this dynamic perfectly. A comet whose behavior challenges our assumptions, whose chemistry hints at alien processes, whose passage near Mars provides data never before collected from a second planetary vantage point. In the end, the story of 3IATLAS is a testament to human curiosity. It reminds us that the universe is unpredictable, that interstellar objects can surprise us, and that even a small comet from a distant star can captivate our imagination. Whether natural or artificial, its unusual activity forces us to ask questions, to measure carefully, and to consider possibilities beyond the ordinary. It is both a mystery and an opportunity, a growth puzzle for science, and a canvas for wonder. 3IATLAS will continue its journey, moving closer to the Sun, flaring unpredictably, approaching Mars, and ultimately leaving our solar system. Along the way, it challenges the line between the expected and the extraordinary, teaching scientists to remain vigilant, open-minded, and creative. In the interplay of speculation and science, humanity finds both knowledge and awe, as we trace the path of a comet that came from another star, bringing with it the mysteries of a distant world, the mystery of its chemistry. Light is more than illumination. It is information. Every photon that travels across the void carries with it a story of the material it has touched, the processes it has experienced, and the forces acting upon it. For astronomers, light is a language, and spectroscopy is the act of translation, splitting light into its constituent wavelengths to decipher the chemistry of distant worlds. And when scientists turned their instruments toward 3IATLAS, the story that emerged was as alien as the comet itself. At first glance, 3IATLAS glowed green. The hue was unmistakable, reminiscent of the familiar green tints seen in many comets within our solar system. Typically, such coloration is caused by diatomic carbon C2 molecules, which fluoresce in the presence of sunlight, creating the ethereal green halo surrounding a comet's nucleus. Yet when astronomers examined the spectrum of 3IATLAS, the expected signatures of C2 were faint or missing entirely. The glow remained, but its source was enigmatic. What chemical processes could produce such a brilliant green hue without the usual culprit? Early spectral analysis provided additional surprises. Carbon dioxide was unusually abundant, far higher than in typical solar system comets at comparable distances from the Sunday. Cyanogen, a rarer molecule, was detected, along with trace amounts of vaporized nickel, a heavy metal rarely released from cometary nuclei. At such distances, the combination was unprecedented. It suggested that 3IATLAS had formed under conditions radically different from those in our own solar system. Its chemistry was a fingerprint of a distant star system, a story frozen in ice and dust for millions, possibly billions of years. The depletion of carbon chains presented a puzzle. In solar system comets, diatomic carbon is almost always present in the coma, giving rise to the characteristic green glow. Its scarcity in 3IATLAS implied either an unusual formation environment or extensive alteration during interstellar travel. Cosmic rays bombard interstellar comets for millennia, breaking apart fragile molecules and altering chemical abundances. It is plausible that over eons, radiation selectively destroyed certain compounds, leaving behind more resilient ices like CO2 and refractory metals such as nickel. The presence of nickel vapor added a further layer of intrigue. Metals do not typically sublimate easily. They are bound within dust grains or mineral matrices. Yet 3IATLAS was releasing detectable nickel at distances where solar heating is modest. This observation suggests that either the comet's structure is highly porous, exposing metal-rich layers to sunlight, or that the composition itself is unusual, possibly including exotic compounds formed under alien conditions. The mystery deepens when considering the comet's green glow in the absence of C2. Could other molecules such as acetylene, C2H2, or cyanide radicals contribute to fluorescence in ways not seen in solar system comets? Perhaps overlapping emission lines create the illusion of a green halo without requiring traditional carbon chains. Alternatively, 3IATLAS may contain entirely unfamiliar compounds capable of producing visible emissions under ultraviolet illumination. Each possibility points to chemistry that is both alien and instructive, offering insight into the diversity of planetary systems. Observations from Mars orbiters provided complementary data. HiRISE and other imaging instruments captured the structure of the coma and faint jets of material. MAVEN's ultraviolet spectrometers recorded emissions from light elements, while TGO's infrared instruments measured volatile release. From these multiple vantage points, scientists began constructing a three-dimensional map of 3IATLAS's coma, identifying regions of active outgassing and areas where chemical anomalies were concentrated. The combination of green glow, unusual CO2 abundance, cyanogen presence, and nickel release challenges the assumption that interstellar comets behave like those in our solar system. It underscores the need to expand models of comet formation, migration, and chemical evolution. The traditional dichotomy of typical versus anomalous comets is insufficient when confronted with a body originating beyond the sun's gravitational influence. Scientific debate has been intense. Some researchers suggest that hidden pockets of carbon could explain the green hue, temporarily shielded from detection but fluorescing at unexpected intensities. Others propose entirely new chemical pathways, enabled by interstellar conditions, that produce emission lines in the visible spectrum. Computational models have been developed to simulate the sublimation of alien ices, considering factors such as porosity, thermal conductivity, and radiation-induced chemical changes. The implications extend beyond cometary science. Interstellar objects, like 3IATLAS, offer a window into the chemistry of other planetary systems, revealing the variety of conditions under which planets, ices, and organic molecules form. Some systems may be rich in complex carbon, providing building blocks for prebiotic chemistry. Others may be carbon poor, creating environments less conducive to life as we know it. Every observation of 3IATLAS informs models of planetary system evolution across the galaxy. Even the smallest detail carries weight. Variations in brightness across the coma suggest heterogeneous composition, with pockets of differing volatiles and metals. Jet structures indicate rotational influences, with active regions exposed to sunlight at different angles. Each nuance is a clue, revealing how a comet born in a distant system behaves under solar heating, how interstellar aging modifies its surface, and how alien chemistry manifests in visible light. Public fascination has mirrored scientific intrigue. Headlines describe alien chemistry and mystery green glow, emphasizing the comet's otherworldly appearance. While sensational, this fascination reflects a deeper truth. Interstellar comets are messengers from other stars, tangible reminders that planetary systems beyond our own are not theoretical, but real, active, and diverse. Yet science tempers excitement with rigor. Data must be reproducible, measurements verified, models tested. The extraordinary chemistry of 3IATLAS is scrutinized, cross-referenced with Earth-based and Mars orbiter observations, and compared to solar system comets. Each new measurement reduces uncertainty, clarifies anomalies, and refines our understanding, even as new questions arise. The mystery of its chemistry is not merely a curiosity, it is a lens through which we view the galaxy. Carbon depletion, CO2 abundance, nickel release, green glow. Each feature tells a story of formation, journey, and survival. Each is a record of conditions far beyond the solar system, shaped by forces and environments we are only beginning to understand. As 3IATLAS approaches perihelion and its closest encounter with Mars, further observations promise to reveal more. Will additional flares release hidden compounds? Will the green glow shift or intensify? Will new jets emerge, altering the chemical map of the coma? Each stage of the journey is an experiment, unfolding in real time, providing data that could reshape models of cometary physics and interstellar chemistry. Ultimately, the comet's chemistry reminds us of both the limits and the possibilities of human knowledge. While we can measure spectra and model outgassing, The alien nature of 3I/ATLAS challenges assumptions, inspires creative hypotheses, and expands the horizon of what we consider possible in the universe. It is a testament to the complexity, diversity, and wonder of the galaxy. A small, glowing traveler carrying the secrets of a distant star system across the void, whispering them to us in the language of light. 3I/ATLAS, in its green brilliance and unusual composition, is a messenger from beyond. Its chemical mystery embodies the intersection of observation, modeling, and imagination. A puzzle that scientists will study for years to come. A reminder that the galaxy is alive with wonders waiting to be discovered. What happens next? The journey of 3I/ATLAS is far from over. Every comet carries a story written in ice, dust, and sunlight. A narrative that unfolds as it approaches the Sunday. Some comets brighten gradually, presenting predictable patterns, while others flare unexpectedly, fragment, or vanish in a burst of dust. For an interstellar visitor like 3I/ATLAS, the possibilities are even broader, each step revealing more about the alien system from which it originated. The question now is, what will happen next as this enigmatic traveler continues its path through our solar system? The first milestone is perihelion, the point in its orbit closest to the Sunday. For 3I/ATLAS, this occurs around late October 2025 at roughly 1.4 astronomical units, just inside the orbit of Mars. At this distance, solar heating intensifies, triggering sublimation of surface ices and volatile compounds. Observers anticipate that the comet's already unpredictable behavior may escalate. Flares, new jets, or increased coma activity could occur. Perihelion is both a climax and a crucible, a moment when the comet's internal chemistry and structure face the full intensity of the Sunday 4. Earth-based telescopes. This period presents challenges. As the comet approaches the Sun from our perspective, it will be lost in solar glare, entering solar conjunction. Observations will become difficult, if not impossible, for weeks. Ground-based instruments will struggle, leaving only space-based observatories, such as Hubble and JWST, and orbiters around Mars, to continue monitoring. The temporary loss of Earth-based visibility adds tension, as scientists know that some of the comet's most active moments may occur when direct observation from our planet is impossible. Meanwhile, Mars orbiters are poised for the comet's close approach. By early October, 3I/ATLAS will pass within 28 million kilometers of Mars, a proximity that allows unprecedented observation from orbit. HiRISE, MAVEN, TGO, and HOPE will record high-resolution images, ultraviolet and infrared spectra, and wide-field imaging to capture every nuance of its activity. This dual perspective from Mars and from Earth, when possible, enables scientists to construct three-dimensional models of the coma, map outgassing jets, and measure chemical abundances with unprecedented precision. The comet's velocity and trajectory also introduce subtle complexities. Hyperbolic motion means that small outbursts can slightly alter its path, creating variations in predicted positions. Tracking these changes is critical for coordinating observations across multiple platforms. Each flare, each burst of gas, each structural adjustment contributes to refining the comet's trajectory and understanding its physical properties. The outburst observed in early September, a 20-fold brightening, foreshadows further activity. Scientists anticipate that perihelion may trigger additional flares, particularly as previously hidden volatile compounds become exposed to solar radiation. Rotational forces may exacerbate this, with active regions of the nucleus responding differently depending on orientation. Modeling these interactions is challenging. They are unlike anything recorded for solar system comets. The chemistry of 3I/ATLAS continues to puzzle researchers. Its green glow, carbon depletion, abundant carbon dioxide, cyanogen, and nickel vapor suggest a composition forged in a star system distinct from our own. As the comet approaches the inner solar system, additional sublimation may reveal more exotic compounds, offering a glimpse into the building blocks of distant planets. The combination of chemical mystery and dynamic activity makes each observation critical. During solar conjunction, scientists rely on orbiters around Mars and space-based instruments to continue monitoring. MAVEN's ultraviolet spectrometer captures emissions from hydrogen, oxygen, and other light molecules, mapping jets and outgassing activity. TGO's infrared instruments measure thermal gradients and volatile release, while HiRISE resolves coma structure and tail formation. HOPE provides wide-field imagery, contextualizing the comet's position relative to Mars and background stars. Together, these instruments create a multidimensional portrait that Earth alone could not provide. By the 19th of December 2025, 3IATLAS will make its closest approach to Earth, roughly 1.8 astronomical units away. This is not an immediate threat. Its trajectory is safely hyperbolic, but it represents the best opportunity to study the comet from our planet. Ground-based telescopes and amateur observers will capture its brightness, color, and tail structure. Space telescopes will complement these observations with high-resolution imaging and spectroscopy. Combined with Mars orbiter data, this represents an unprecedented chance to study an interstellar object at multiple points in space simultaneously. The comet's survival through perihelion is not guaranteed. Comets often fragment under thermal stress or break apart due to internal pressure. Observers, watch closely, hoping 3IATLAS remains intact. Even if it fragments, however, this too would provide valuable data, the distribution of material, the behavior of debris, and the dynamics of outgassing in real time. Each potential outcome offers insights into the composition, structure, and resilience of interstellar bodies. Beyond science, the encounter captures the imagination. Public interest has soared, with headlines emphasizing the comet's alien appearance, unpredictable flares, and passage near Mars. People are captivated by the idea that a fragment of another star system, traveling light years across the galaxy, can be observed and studied from multiple planetary platforms. It is a tangible reminder that the universe is vast, interconnected, and full of surprises. This event also informs future mission planning. The upcoming Comet Interceptor mission is designed to rendezvous with interstellar objects, and the observations of 3IATLAS provide critical benchmarks. By analyzing its trajectory, outgassing patterns, and chemical composition, scientists refine models that will inform spacecraft design, observation strategies, and mission timing for future interstellar visitors. As 3IATLAS moves past Mars and the Sun, its brightness will eventually diminish. Its hyperbolic path ensures it will leave the solar system, never to return. Yet the data collected during this brief passage will leave a lasting legacy, shaping our understanding of interstellar chemistry, cometary physics, and planetary system diversity. Scientists will study this comet for years, teasing out insights from its composition, activity, and trajectory. The event also highlights humanity's growing reach into the cosmos. Mars orbiters, Earth-based telescopes, and space-based observatories combine to track a tiny object moving through the vastness of space. It demonstrates how planetary science and astronomy can converge, using one world as a platform to observe a visitor from another star. The collaboration across countries, instruments, and missions exemplifies the collective effort required to study such rare phenomena. Ultimately, 3IATLAS serves as both a scientific opportunity and a philosophical reminder. Its journey from a distant star, its unpredictable flares, its chemical mysteries, and its near pass by Mars emphasize the dynamic nature of the galaxy. Each observation is a testament to human curiosity, ingenuity, and the desire to understand the unknown. Even as it departs, the comet leaves behind data, insights, and a renewed sense of wonder about the vastness and complexity of the universe. What happens next is uncertain. Perihelion may trigger additional flares, the nucleus may fragment, unexpected chemistry may emerge. Each possibility is an experiment unfolding in real time, offering insights that extend beyond this single object to the broader population of interstellar visitors. And while the comet's path will carry it away forever, its legacy in advancing our understanding of the cosmos is secure. The story of 3IATLAS is far from complete. Its brightening perihelion close approach to Mars, and eventual departure provide a narrative of cosmic discovery, bridging the gap between Earth and Mars, solar system, and interstellar space. For scientists and the public alike, it represents a rare, fleeting, and extraordinary glimpse into the workings of the galaxy. And as the comet continues on its path, humanity watches, studies, and learns, ever mindful that the universe still holds countless secrets waiting to be revealed. A rare visitor. The universe is vast, a stage of unimaginable scale where stars burn for billions of years, planets orbit quietly, and most comets never venture far from their birthplaces. Yet occasionally, a traveler appears that defies expectation. A fragment from another star system, a comet hurtling through interstellar space, crossing into our solar system for a brief, fleeting moment. 3I. Atlas is one such visitor. Its appearance is rare, its origin alien, and its behavior unpredictable. Glowing, flaring, chemically exotic captivates both scientists and the public alike. Rare, in this context, is literal and figurative. Interstellar comets are extraordinarily uncommon. Oumuamua, detected in 2017, was a fleeting point of light that challenged our understanding of cometary physics. Borisov, in 2019, resembled a more typical comet, yet still carried traces of alien chemistry. Now 3I-ATLAS has arrived, the third known interstellar object, but its unusual brightening, green glow, and chemical anomalies mark it as a singular event in human observational history. Rare also means precious, a once-in-a-lifetime opportunity to study matter formed around another star, traveling for millennia to reach our neighborhood, and passing by planets we have long studied. As 3I-ATLAS approached Mars, humanity's observational network expanded into unprecedented territory. Mars orbiters MRO, MAVEN, TGO, and HOPE turned from the planet's surface to the void, capturing the comet from a second planetary perspective. High-rise resolved structures within the coma. MAVEN measured ultraviolet emissions, TGO detected temperature variations and volatile release, and HOPE provided wide-field contextual imaging. Earth-based telescopes complemented these observations, creating a multi-dimensional portrait of the comet's behavior. For the first time, an interstellar object was studied simultaneously from two planetary vantage points. The comet's chemical anomalies underscore its alien origin. Its green glow is visible, yet the expected diatomic carbon molecules are weak or absent. Carbon dioxide is unusually abundant. Cyanogen and nickel vapor appear in unexpected ratios, and fluctuations in brightness suggest active processes beyond simple solar heating. Each observation tells a story of formation, interstellar journey, and survival. Unlike solar system comets, 3I-ATLAS carries the fingerprint of a distant star system, offering humanity an unprecedented glimpse into the chemical diversity of our galaxy. Its sudden 20 times brightening demonstrates the dynamism of interstellar bodies. Unlike predictable comets that gradually flare as they near the Sun, 3I-ATLAS surprises. Jets of gas and dust erupt unpredictably. The coma swells and shifts, and subtle rotational effects may influence outgassing. Each flare and emission provides clues to the comet's internal structure and composition, allowing scientists to reconstruct its activity in real time. The outbursts are not mere spectacle. They are windows into alien processes frozen in time and space. Beyond the science, 3I-ATLAS captures the imagination. The public marvels at the notion of a comet from another star, glowing green, approaching Mars, flaring unexpectedly. Headlines describe it as an alien visitor or messenger from the stars, feeding curiosity, wonder, and a sense of cosmic connection. These reactions remind us that the universe is not merely observed, it is experienced. Objects like 3I-ATLAS bring the galaxy closer, making tangible what is usually abstract. The vast distances, the long journeys, and the interconnectedness of planetary systems. Speculation about the comet's nature, while sensational, underscores a fundamental truth. The unknown inspires exploration. Some suggest its unusual behavior could hint at technology, while others imagine exotic ices producing unexpected emissions. Scientists, however, remain grounded in evidence. Observations are measured, models tested, and conclusions drawn from data. The interplay of speculation and science drives inquiry, encourages creative hypotheses, and pushes the boundaries of understanding. 3IATLAS embodies this delicate balance, offering both concrete measurements and a canvas for imagination. The comet's close approach to Mars adds another layer of significance. By providing a vantage point beyond Earth, the orbiters capture data inaccessible from our planet. Structure, jets, rotational effects, and chemical gradients could all be analyzed with unprecedented clarity. This dual perspective demonstrates the value of extending observational networks into space, a glimpse of humanity's growing ability to study the universe not from one point, but from multiple locations simultaneously. As 3IATLAS moves past Mars and perihelion, it will eventually fade, continuing on its hyperbolic trajectory out of the solar system, never to return. Its departure is inevitable, a reminder of the fleeting nature of cosmic encounters. Yet its legacy is enduring. The data it provides informs models of interstellar chemistry, cometary dynamics, and planetary system evolution. Its passage illustrates the diversity of exoplanetary systems and the ways in which material circulates across the galaxy. Even as it disappears, 3IATLAS serves as a reminder of humanity's place in the cosmos. We are observers, interpreters, and explorers, capable of detecting, measuring, and understanding fragments of distant worlds. The comet's journey bridges light years, connecting our solar system to alien environments and offering insights that extend far beyond its brief appearance. Its path through space is a story of cosmic migration, chemistry, and survival, a narrative we are privileged to witness. The story of 3IATLAS is also a story of human ingenuity. Earth-based telescopes, orbiters around Mars, and space observatories were coordinated to observe this tiny visitor. Scientists collaborated across continents, sharing data, refining models, and planning observations in real time. The event exemplifies the collective effort required to understand the cosmos, demonstrating how curiosity, preparation, and technology converge to reveal the universe's secrets. Ultimately, 3IATLAS is a rare visitor in every sense. Rare because interstellar comets are seldom detected. Rare because its behavior, chemistry, and trajectory defy expectations. Rare because its passage near Mars allows a perspective never before available. And rare because such moments a comet from another star observed from multiple planets may not recur in a human lifetime. It leaves a legacy beyond data and images. It inspires awe, curiosity, and humility. It reminds us that the universe is alive with motion and diversity, that our solar system is not isolated, and that even the smallest interstellar fragments can carry profound scientific and philosophical significance. 3IATLAS, a fleeting point of green light in the sky, has become a symbol of exploration, discovery, and the boundless possibilities of the cosmos. As it drifts outward, fading into the interstellar darkness, humanity is left with knowledge, questions, and wonder. Its journey is a testament to the interconnectedness of the galaxy, the unpredictability of celestial objects, and the enduring human desire to understand the unknown. The rare visitor has come and gone, but its story will resonate for years to come, reminding us of the galaxy's vast mysteries, the elegance of cosmic mechanics, and the endless curiosity that drives humanity to look up, measure, and marvel. 3IATLAS, in its brief passage through our skies, has bridged worlds, inspired inquiry, and ignited the imagination. It will not return, yet its presence leaves an indelible mark on science, exploration, and the human sense of wonder. In observing it, we are reminded of the scale, beauty, and mystery of the universe, a vast stage on which rare visitors pass, leaving behind data, inspiration, and awe.